let's look up the word cantilever. The cantilever, as soon as it loads, is fixed on one, but I'm calling it like the cantilever effect. The rigidity is created by the reinforcement, just by default coming off of a position, a shelf, a wall, a column head. The rigidity there creates a cantilever effect. Now I'll support that in just a second, I guess.
Cantilever.
Okay, just a little delay in my computer here. A long projecting beam or girder fixed at one end used in bridge construction. All right. So now we go to, let me get rid of that, right here. So we look at, I'm being tricky. Confirmed trees exist. Okay, this here. Oh, back here. Box and slab extended from wall. Look at that. Box and slab extended from wall. That acted in a cantilever fashion. As this went down, this cantilever fashion from this wall system was so rigid, including the box on top of it. So everyone wanting to find that box, it fell from the box. Well, why didn't this box fall? If the box are so, so heavy and so naughty, if you will, building falling all around it, how come this box didn't fall? How come the deck around it fell? Well, we have a couple of things there, but right here, I think I'll do this one. So here's my cantilever here also. But this is that box, the planter box. There's the hallway. There's roughly the column. There's the vehicles below. That's the wall system. And right here is that crack. And after I posted this crack in there, NIST put out a notification asking everyone to please send in images. You don't know what you have. You might have something in the background. So that was interesting. So NIST is monitoring the channel. But hopefully they won't get stuck on stupid with the narrative that they must come up with global warming, sea level rise, because the government wants that. It's just a matter of integrity, and these people lack integrity if they just do something like that. Here's the crack, right? This crack was indicating that there's a deflection over here. That biasly so back to my column that I point at in the video I just released. I'll link it below. The last one, I show you the sagging, the load stresses around the one column there. But now I'm profiling it for you, working my way into showing you. I know where I'm going, but I'm working my way into showing you how you need to profile the entire cracked up system, including the core samples. Remember, there's a core sample over here that's fractured. And that's right about, here's the car, so it's right next to a car, right about there next to a car, below, at the deck area. And then right here on the deck is this fracture plane. If I follow this fracture plane, it goes in front of it goes in the critical shear area of the column head, and it comes across right about where we have the core sample. It's junk, put it plain English. And so to get that junk, we've got to get separation of the concrete. We've got to get some shear planes, some like plywood, if you will, for shear planes in this capacity. How you laminate the sheets together. Well, we're getting some shear planes, and that's a much deeper video, but I'm getting there for you guys about why you need to stop using plate slab systems. I consider this a bridge deck, not just a pool deck. It holds the cars drive on it, and this is the walkway for the people, next, right, connected to the bridge deck. So it's just a bridge deck with a walkway that happens to be larger. Tell me how it's not. And you get to park on this bridge deck and throw parties on this bridge deck. All right, so on this bridge deck, you can ignore cracks for some reason. The cracks are unknown is what, and I don't know if he was mentioning these cracks or not, but the Morbido report, pronunciation as I stated, maybe these are the cracks he was talking about, and he couldn't understand that it was in a critical shear area. All you gotta do is put the cracks put the cracks, superimpose them over your drawings, and then think about where they are. Are they in the critical shear zones? Are they in the tributary zones? Are they from a foreign object hitting them? Are they from buckling. If they're from buckling, well, of course, you've got some deflection going on there. What's causing the fractures? Are they just a manufacturer defect that when they bought these tiles, they laid them there and they dried out over the time, even more time, and they shrank and cracked? Well, this is in a shaded area. It's in the same plane, so this, the lines, I guess, sharing from one to the next. It's not like they all cracked in the middle. No, you can see the directions of this crack. And as you take it back, we're in the critical shear zone, right outside there, sort of like the other one that was over there they showed with the rotation box. Right about there. The rotation down here is similar to the rotation down at the planter box. So we have multiple rotations down. This shows the shear plane. It was already fractured enough where it couldn't engulf it, pull it over. This is very interesting for you to know. If this couldn't pull this down because it's in place, what makes you think that it could pull down this glass room over here? Well, it didn't. Well, what makes you think if it can't pull this down, it can't pull this down? Why would it pull down over there by M&L? Think about that. Why would that? This is what I've given you many times, and I would hope that some engineer would catch on. This is the chair. There you go. What's the significance of that chair? There's the wall. Let me give it away now. What's the significance of this rebar here? It's a marriage. With a marriage, you need one person, or do you need two? There's a hint in that big, huge hint I'm giving you there. This is a marriage. This rebar is a marriage. There's a hint there, a huge hint. All right, I'm giving it away in this video. I talk about anchor, that it's an anchor. I wanted an engineer to say something, to say, oh, I see your anchorage there with your system, and now I've got to just do it myself. I'm not proud to do this myself. I hope to get caught when I do my things to go, oh, you're outstanding to someone that you actually are learning, that you understand. All right, this is like the slab. All right, and this is the slab. Now let's go ahead and put the slab on top of this wall. And then I showed the rebar come up, and I talk about how it bends over, right? It fractures over right here. I show that in videos. And I'll talk about this piece here that's left behind. Now, how is that piece left behind? How is that even possible? If the rotation is here, that piece comes out with it, doesn't it? Where it fractures and leaves all this piece here, a much larger section of blowout. But we already have the steel here. So how would it do that? How would it do that? Well, if you guys are paying attention, and you guys, a lot of you are engineers, and a couple of you are structural engineers watching me, so I find it very interesting that you're not, that no one has called me out on this. And I'm still giving it to you. I was going to I do have a photograph. I was going to post this photograph and do this long video. Hey, check this out. I drop clues and then I disappear. I was going to drop a clue, disappear, and let it soak in, and lean back to these videos again, back and forth. I'm giving you a clue right now. Go back and forth, and maybe take a week, a month, maybe 2 months to do it, maybe 3 months. Maybe I'll never reveal it until 3 years from now, but I'm going to reveal it now. It's a marriage. In a marriage, you always need yin and yang, the opposites. So this is the front steel that's sticking up. I just said it. So there must be some back steel back here. Let's look. I think I see it right there. Not the back steel, right here. Wait a minute. Is it right there? Right there? I'm playing around, guys. Here it is. Oh, there it is. Right in front of you. Right there, the back steel. There's two steels. All right, let me just cut to the chase there, anticlimactic. There's two pieces of steel. All right, so when this rotates down, this is your anchor point here, along with your hooks coming this way. Now, I know you're not supposed to hook. Your hooks on the bottom are really not thought of, but you need development length. This is only 9.5 inches. So they do allow for development length that you can put hooks on the bottom. Don't save. Now, somebody might get triggered by that. No, you don't do. It's development length we're talking about here. L bent rebar 90 degrees as plans call for. You understand that's bottom steel? That's bottom steel with the 90 on it, with the L on it. So it's not top steel. Top steel's up here. And there's some I believe, well, was this 90 degree or straight? And you can see the kinks in them right here and here and here. Again, the 90 degrees appear to be bottom steel here. So it appears that this architect and engineer and contractor did development length using 90s at the bottom. This is biased. I don't really have the full detail of this, but I do know what I'm looking at here. That this is rebar at the beam, if you will. Stirrups, bottom steel, and below the bottom steel, as you can see right here, this is not above it. Below the bottom steel are, and coming out of the floor over there, is 90 degree bent bottom steel. So that helps with that reaction at the wall where I show the push-pull, the tugging, the separation, the shearing action. So if Nis is watching this, and apparently you do, you can now give this to your engineers and say, okay, we see something here. Now, I know I'm wishful thinking is silly of me, but it's not. It's silly meaning it's not the way the world works. But I would hope that this would come out, and you could still get your global warming in there somehow, but that you release it. This how the shear plane actions happen once you get deflection. Again, the testing for punching shear is incorrect. Okay, so here's a punching shear test part 2. Let's go with this one. I have not seen it, I don't think. I've seen this image. All right, so they use a driving force, and you see this is anchored down. They anchor the pad down, and then they drive the column, if you will, up. And that's their version of having the same effect as punching shear. Well, it's not. It is not. The pad's deflection based on load would create okay. Imagine this is all paper around here, and you start ripping down, pulling down on one side because it deflects on one side. Why? Because your spans are greater on this side of the paper than that paper. Your spans are these are your column heads, right? They're close together. Well, in real life, these columns are offset. And so a greater span is going to have more deflection, being that they didn't beef it up or change the profile of the deck. It's going to deflect more than the shorter spans will. So with that said, the greater spans deflecting more create more of a moment, a stress over on let's say this side. Let's see if we have a better image. Okay, to screenshot over. Oh, okay. So let's run this one, and it says punching shear test. Okay, so they're pushing up. Okay, so they just pushed up, and there's our first major fracture. Even it wasn't in equilibrium. It kicked this one side up first. It fractured this side first. And there's just back to its point of anchorage, the part that ties down. But our deck is not doing this. It's not tied there in one section there, and these are tied there. There's an actual deflection going on, as I talked to you about. Let's screenshot that and let's show you the deflection. Yes, so engineering is really a bunch of idiots that are teaching this. Save myself. I'm not that much of an idiot. I'm more of an asshole. So the bunch of idiots teaching this, and then it propagates. It gets published, and then they're like, oh, okay, got it. Yep, we can extrapolate from there. But this is wrong. The column is here. All right? Just put the column here. Separate it in your mind. There's the column, and this is the pad above it. All right? And this is the pad. All right, let me just grab this. Now, and there's a true point there and a true point here. In other words, These are this. Let me, if I can do this. I'm just going to use a little. I know it's not lined up perfectly, but let's use perforation like that. All right, if you let me have my little liberty. All right, so there's the pad's on top of there, and the transfer from this part of the pad is 1-to-1, directly down, until you get deflection. If you get a load going this way, because you're another column here. Let's put a column over here, and I only put a partial column that you can see. All right, then let's drag it down. Too ugly. Let's do this. Okay, so now with this profile, this is a 1-to-1 direct. And look what we have here, the fracture wise. Yeah, it's solid. Okay, so it's kind of 1-to-1 direct, except for here's this angle here and this angle here match it. They match. So this fracture, whoa, daddy. This fracture here and this one are symmetrical. Whoops. Are symmetrical. This spacing here and here. Okay, let's go ahead and get rid of one. I'll leave you one. On this side, now let's do what it really would look like. Based on reinforcement, it would probably be critical shear zone, making that cantilever effect. Remember the planter box. Over here also would be a planter box, if you will, the cantilever, right? And here. And then this section between these two, of the tributary area, are the areas that are more susceptible to, depending on the greater the span between these, more susceptible to sagging. On this side also, they got this whole thing, I guess, hogging. Since this is going up, driving this up, they're actually doing this. Since these are pinned at the ends with these tie-down bolts. See the giant bolts? So they're actually just doing that. And that's not the way this fails. It's actually opposite of that. Here's the column head. The sagging goes on. There's the head. And let's say the head doesn't sink through subsidence. I'm being facetious. And here's another column. So it looks like... let's do this. So it looks... Here's your drape. Let me put a column here. And I'm only going to do the single, just give you the drape idea. I won't do the double up stresses and all that. How I told you, force multiplier over there. Don't want to get you distracted. But this is what it looks like. The sagging takes place pulling down on the outside critical shear zones here, pulling down on them. And then we get the fractures. The fractures look similar to at the planter box, the one I showed you with the car with the fracture above it, the one that's by the cars, because the sagging takes place, you get an open fracture right about where this can pick up. Where I'm saying where this, because depending on how it's going to be rigid by the column, how much rigidity depends on how much steel they put there. In this case, we can see the symmetry here. There's this little horseshoe here, this little horseshoe here. Let's see, do we have a secondary fracture in here? I don't. No. This is driving up, obviously, the concrete behavior with the steel behaved a little differently over here. I don't know what they're doing there. With that said, let's see if it will never, I'm sorry, it will not balance here. It will start torquing, and let me see. So now that it's freed here, this should probably finish breaking and maybe torque and give a different fracture down here. Let's see if they show it. Because it's a different load path. Yes, there it is. So it's a different load path now. Because this is already broke, so it's going to fracture. It's still anchored with rebar, but it's going to torque. It's going to put it on an angle now, and as it lifts up, and there's a fracture. Let's do this. One more time. And one more time. Let's YouTube it, because I can second it. Great. So bear with it. It's very interesting. As long as my mic is working. By YouTube. Wow. Okay. Now. Yeah, so there's that that crown I talked about. Well, that's not the way this thing behaves. This doesn't drive up. It's not the same. They're extrapolating this. Extrapolating incorrectly. And it's not just this engineering group. It's many schools and everything. They'll put it on top and drive it down. It's still not the same. Deflection is taking place between the two zones. You need to load it between there with some steel beams, perhaps, or like a car, and then put a car there and then load the fucking car up with the tires in place and load it as it will be in real life. Not this. I do like that. Wow, wow, this is amazing. Looks like stirruped it, which is really not going to be something that's going to be seen there. I wish I knew exactly what they consider this model. Let's go back. That's why it stuck. It was so it stuck together so well. They had stirrups in it. Okay, let's do this. I'm looking at the fracture develop. How it widens. You see a drop down. Oh, it had a spring to it. See it? It's up. It's down. So this is useless because you won't be able to see the fractures like this. The way they reinforced it is craziness too. They also secured it, looks like, in the back and 3 other additional points. And they didn't do it here. They just left it open. So there's, as you saw, there's this a torque. One end of it comes up. It's tied in the back. The anchorage back here. There. I guess there's a bolt there. So this is it's stupid. These tests are just, it's 132, just stupid. Let's take another look at this one. Another one. Have you guys seen these United Spot? Oh my gosh, it's crazy funny. All right, see again, they're driving it up. Let's watch it. And so there's your securement, and now you're getting this flex this direction. As you see, this isn't flat. There's no choice but to flex. This might have the reinforcement on it also, but you're getting uniform fractures on this face. And these are just crack sensors or load sensors, and it's ridiculous. Okay, so now as it's driving up, where it's separating the bottom half of this pad with the top part of this half in symmetry. See the mustache here, a little mustache there, and there's our obviously our column right below it going up. And it's driving, and the steel can't hold on, but the bottom steel is acting like a little bit of a beam action there. Remember but it's fracturing here to here. So it's going to rotate up and away also. And there's up and away from us. Oh, now they remove the, well, look, I don't know if that's there or not. Yeah, they removed it just to lift it up so they can inspect it, I think. And then just a dead load of it, and trying to hold together with the steel just cause it the spalling. Pretty much interesting, but useless. This is not how this fails. There's a steel there, and this is the steel I'm talking about that I would love them to see them do, but this is never going to happen. It's never going to happen. It's too expensive, and I mean it looks like the steel. I don't know if it is or not. Actually, it's too long. See how it's too long all the way across the stirrup system? They should have made shorter pieces. This is too long. In other words, in Gulf 2 and then in Gulf 3, it's big way to try to share the stirrup system over. It's a big, and same results. Oh, there's their gauges. This will tell the deflection. But they're driving up. They're driving it up. It's not the same. It's not the same